In this video, we're going to be talking about antiderivatives. So earlier on, when we were first working with functions and derivatives, what would happen was we would be given a function, say f of x, and then we would take the derivative of f of x, and then that would leave us with the derivative we could write as f prime of x. We'd be given a function, we'd differentiate, and then we'd end up with the derivative of the function. Now we want to go the other way. Now if we're given a function that, we could have taken the derivative of to get f prime of x, but we're given a function. Now what we want to do is take the antiderivative, and then that'll lead us back to some original function, f of x. And we're writing this as f, capital F here. Okay, so it's as though we're going in the opposite direction from a function, and we're going to take the antiderivative and lead back to some original function. Alright, so what we say is a function f, here I'm writing this as capital F, is an antiderivative of f if f prime of x is equal to f of x for all x in the domain of lowercase f. So as a quick example, if we took the derivative of x squared, well, we know that that would give us 2x by the power rule. So what we'd say is an antiderivative of 2x is x squared. Okay, so before we'd go from x squared, we'd take the derivative using the power rule. That would give us 2x. So if we go the other way, if we start with 2x, we'd say, well, an antiderivative of 2x is x squared. So using the notation that we were using in the previous slide, we'd say 2x is f of x, or lowercase f of x, and x squared is f, capital F prime of x. Okay, so we can think of antiderivatives. I mean, anti just means the opposite of something. So antiderivative is kind of like the opposite of the derivative, or we're going the opposite direction of what we were doing when we were taking derivatives. Now we're saying that this is just one of the one of the antiderivatives of 2x. Now if we think about it, so if we take the derivative of 2x, if we take the derivative of x squared, let's say plus 5, that still gives us 2x. If we take the derivative of x squared plus, 27, that also gives us 2x. In other words, if we take the derivative of x squared plus any constant c, that gives us 2x. So when we're thinking about finding the antiderivative of something like 2x, we always need to account for the fact that in the antiderivative there could have been a constant there. So what we say is that the antiderivative of 2x, the antiderivative of 2x is, how we want to write that is x squared plus c. Okay, so we want to account for this constant term c here. Another way of saying this is all of the antiderivatives of 2x are represented by x squared plus c. Alright, so in the next example, let's find all the antiderivatives for the following functions. Okay, so first we have 3x squared. Now, on the previous example, I didn't really explain how we got the antiderivative, But what we want to do is we can, it's kind of like going backwards from the power rule for something like this. So the power rule tells us we take the exponent, we multiply that by the coefficient, and then we lower the exponent by 1. So now we're going to kind of go about this in the opposite direction. So if we raise the exponent by 1, and then whatever that new exponent is, we're going to divide by that exponent. So this coefficient remains the same. So 3x cubed divided by 3, and then we can cancel out the 3's, so we end up with x cubed. So x cubed is what we get when we take the antiderivative of 3x squared. And if you're unsure of this, just test it. Take the derivative of x cubed and see if we get what we started with. So d dx of x cubed, and yeah, by the power rule, that gives us 3x squared. So the antiderivative is going to be x cubed, and then we're going to add that, or add the constant term to it. So x cubed plus c is what we end up with here. All right, next let's look at f of x is equal to cosine of x. So we're going to say since the derivative of sine of x is equal to cosine of x. Okay, so if we want the antiderivative of cosine of x, we want to go backwards like this. So we're going to end up with sine of x. So the antiderivative here, we're going to say sine of x plus the constant c. Okay, and again, if you're unsure, take the derivative of what we ended up with, sine of x plus c, and we'll see that we end up at our original function. All right, next we have f of x is equal to e to the x. Now if we take the derivative dy of something, that ends up with e to the x, and if we take the derivative actually here of e to the x, we end up with e to the x. Now remember, the derivative of e to the x is just itself, so going the opposite direction, we still have just e to the x. So the antiderivative is going to be e to the x, and then we need the constant term. And then the last example in this set, we have f of x is equal to 1 over x. So you want to think, if I were to take the derivative of some function, what function, when I differentiate it, will end up with 1 over x? So which function, when I differentiate it, will lead to 1 over x? And that function is ln of x here. So the antiderivative is going to be ln of x plus c. And again, take the derivative of ln of x plus c, and you'll see that we end up with our original function. So we want to be able to use certain notation when we're taking antiderivatives, and there's a few kind of definitional terms we want to be able to use as well. All right, so for an indefinite integral, this is what we're going to use. This is the idea we're going to use for notating what an antiderivative is. So if capital F is an antiderivative of the function f, we say that capital F of x plus c is the most general antiderivative of f. And we write it like this. So a couple of things about what we have right here. So this symbol is called the integral symbol. All right, and then this d of x right here is called the differential. And we saw differentials earlier in the course. Now, that dx, the x right there is telling us what is the variable of integration. And this will make more sense, variable of integration. This will make more sense as we start using this notation more and more. So between the integral symbol and the differential, that contains the function that we are taking the the integral of, or the antiderivative of. So we call the function in here the integrand. Okay, that's not super important that you know that that's called the integrand. We just need to know that whatever's between the integral symbol and the differential contains what we're taking the antiderivative of, or what we're integrating. Okay, and then, so the integral symbol and the differential, if we have those two things, whatever's in between those, that tells us what we are finding the antiderivative of, and then the antiderivative is just over here. Okay, so the language we use when we have a problem given to us with an integral symbol, so we say finding the antiderivative say is we're integrating. Okay, so if we say let's integrate this function, that just means find its antiderivative. So in the next examples, let's verify that each statement is correct. So our first statement, we have the integral of x times cosine of x dx. Okay, we want to see, does that equal x sine of x plus cosine of x plus c. So to verify this, we just take the antiderivative, and we want to take the derivative of that and see if we end up with the integrand over here, with this function. So we're going to say d dx of x times sine of x plus cosine of x plus c. So let's take the derivative of that and see if we end up with the integrand. So first I have a product here, so we're going to use the product rule. The derivative of x is 1 times sine of x plus x times the derivative of sine of x, which is cosine of x. Okay, then the derivative of cosine x is negative sine of x. Then the derivative of c is just 0. So what we have here is positive sine of x and negative sine of x, and we're left with x cosine of x. And that does match with what we had here in the integrand. So we're good. We verified that one. Next, let's say we have the integral of x times e to the x dx, and let's show that that is equal to x e to the x minus e to the x plus c. So again, we'll take the derivative of the antiderivative and see if we end up with our original function here. Okay, so d dx of x e to the x minus e to the x plus c. Okay, so again we have a product right here. Let me use a different color. We have a product right here. So we're going to say the derivative of x is 1 times e to the x plus x times the derivative of e to the x. Well, the derivative of e to the x is just e to the x minus the derivative of e to the x again is e to the x, and then the derivative of c is 0. And I can put plus 0 just so we know we're not forgetting about the c. And then we see we have a positive e to the x and a negative e to the x, and we're left with x times e to the x, and that is what we started with. So we're in good shape there. Now let's look at 3 different properties for indefinite integrals. And before we get to that, I just want to say why we're calling these indefinite integrals. So these are called indefinite integrals because we don't know what that c value is. Later on, we will be working with definite integrals, where we will end up with one specific function that doesn't have a general constant term c. So for right now, we're dealing with the constant term c, but later on we will start working with definite integrals. So we have 3 different properties to look at. We have the sum indifference property of indefinite integrals. We have the constant multiples, and then the power rule for indefinite integrals. All right, so let's let f, capital F and capital G, be the antiderivatives of lowercase f and lowercase g, respectively, and k is any real number. So if we have the integral of f of x plus g of x, we can rewrite this as the integral of f of x dx plus the integral of g of x dx. Okay, so if we have the integral of a sum, we can take the integral of each individual term, okay? And not just a sum, but if there's also a minus sign in between the two functions, okay? So what we'd end up with is just the antiderivative of f plus or minus the antiderivative of g, and then plus the constant term c. Okay, so this rule is just telling us if we have multiple terms separated by plus or minus sign, well, I guess that is what a term is, but if we have multiple terms in our integrand, we can integrate each term individually. The constant multiple property says if we have the integral of some real number k times f of x dx, what we can do is we can factor out the k from the integral and then integrate the function. So it's kind of like what we saw when we had limits. If we had a limit with a constant coefficient inside the limit function, we could factor that out. So that's what we're doing here. So what this would be when we actually find the integral is k times whatever that antiderivative is plus c. All right, and then the last rule is the power rule. So if we have the integral of x raised to the n power times d of x, what we do, I mentioned this earlier, but we raise the power on that exponent by 1, and then we divide by whatever that new exponent is. And then we add the constant c. So I'll do a quick example of this one. So if I have the integral of x to the 5th dx, well, by the power rule here of integrals, we're going to raise that exponent by 1 and then divide by whatever that new exponent is. Okay? And again, if we were to use the power rule to find the derivative of this new antiderivative, well, we'd say 6x to the 5th divided by 6, the 6's cancel, and we end up with what we started with. So the last thing in this video is let's just look at a few more complicated indefinite integrals here, and we'll be using these properties. So first we're going to say the integral of 5x cubed minus 7x squared plus 3x plus 4 d of x, or dx. Now, you'll notice how I wrote the function in parentheses. What we saw previously was when we have the integral symbol and this d of x, whatever's in between those is what is getting integrated. We could have written this, if this was written, I should say, like this. Well, in this instance, only this part is our indefinite integral. We would not be taking the integral of 3x plus 4 because 3x plus 4 is not between the integral symbol and dx. So we can think about the integral symbol and dx kind of like our set of parentheses around whatever function we are finding the antiderivative of. Okay, so I'll use the sum and difference rule here. Pretty soon we won't be doing this every time, but what we could do is we could take the integral, or separate this polynomial that has 4 terms into 4 individual integrals. So 5x cubed dx minus the integral of 7x squared dx plus the integral of 3x dx plus the integral of 4 dx. Okay, so we can split this up into 4 different integrals, and that was the power rule. And then using the other rule, the constant multiplier, or the constant multiples rule, in each of these, well, the first 3 integrals, I have a constant multiple. So 5 times the integral of x cubed dx. Okay, so it's as though we're factoring out the 5 minus, let's factor out the 7 plus 3 integral x dx, and then plus, we could factor out a 4 and write a 1 inside the integrand, but I'm just going to leave it as 4 dx here. All right, and then lastly, we'll use the power rule for integrals. So again, what the power rule tells us is whatever the exponent is on the variable, raise it by 1, and then whatever that new exponent is, that's what we divide by. So here I'm going to have 5 times x raised to the 4th power divided by 4 minus 7 x squared, so x is going to get raised to the 3rd power divided by 3 plus 3x. Right now x is getting raised to the 1st, so it's going to be squared divided by 2. And then here when we just have a constant, what we do is right now there's no x variable there, but you can think of it as x getting raised to the 0 power. So this is kind of like 4x to the 0 power dx, right? X to the 0 is just 1. So I need to raise that exponent by 1, so it's going to be 4x to the 1st, and then dividing by 1, right? We could write it like that, but raised to the 1st and divided by 1st is inconsequential, so we'll just write it like that, and then we need the constant term. So that is what happens when we take the integral of that function. All right, next we have the integral of 4 divided by 1 plus x squared times dx. So I'm going to factor out the 4 here. I'm left with 1 over 1 plus x squared dx. And hopefully this looks familiar to you. This is the derivative of the inverse tangent function. Okay, so when we take the integral of 1 over 1 plus x squared, that is just equal to the inverse tangent of x. So the antiderivative of 1 over 1 plus x squared is tangent inverse of x. So we end up with 4 times tangent inverse of x, and then we need the constant term c. All right, and then our last example here, we have the integral of tangent of x times cosine of x times d of x. Sorry, times dx. Now, what we'll do is we'll rewrite this. We'll rewrite tangent as sine of x over cosine of x multiplied by cosine of x dx. And what we see is that we can cancel out the cosine of x here. So that simplifies the integrand to sine of x dx. And so the antiderivative of sine of x is actually negative cosine of x, because when we take the derivative of cosine of x, we end up with negative sine of x. I'll write this over here. Negative sine of x. So the derivative of negative cosine of x is equal to sine of x, which is what we want here. Okay, so we end up with negative cosine of x, and then we need that constant term c.